Hello students and welcome to this calculus video. In this video, we're going to be looking at the connection between continuity and differentiability. What does that mean? This is going to be a two-part lesson, a two-video lesson, so let's get right into it. So here I said we're going to be looking at the relationship between continuity and differentiability. So if a function is continuous at a particular value of x, does that imply that it is also differentiable? Like, that's the big question. And hopefully by the end of these two videos, you'll be able to say whether that is true or not. And then conversely, if a function is differentiable, does that mean that it must also be continuous? So we're going to be looking at those two ideas, okay? So in this first one, what I want us to do is let's go ahead and start this by saying, okay, let's consider this function the square root of x squared minus 4. I'm going to really look at it at 2. And so the first thing that we want to do is sketch the graph. Put it into your calculator and let's sketch the graph. And when you do that, you're going to get something that looks like pretty close to that. All right. So based on the graph, is the function continuous at 2? And as we're looking at these two things, so we're looking here at the point 2, and you want to go back to our definition for continuity, okay? So looking at your definition for continuity, there needed to be a couple things. First, okay, f of 2 is defined. So f of 2 is defined, so f of 2 equals 0. All right, so that makes it defined. So that was the first thing. You see it right there. It's a solid circle, so it is defined, okay? And the second part of our definition was that the limit from both sides, so as it's matching up, right, from both sides, it needed to also equal the exact same thing. And you're looking at my fingers like, I'm not exactly sure what to do with my left finger because like there is no left hand limit. So as I'm looking at it, the limit of f of x as x approaches 2 from the left does not equal the limit of f of x as x approaches 2 from the right. So therefore, the limit of f of x as x approaches 2 from both directions does not exist, okay? So what we want to say here, therefore f of x is not continuous at x equals 2. All right, and we can see that in our graph, right? It only has a right-hand limit. It doesn't have a left-hand limit. So let's go on and look at the next part of it. So now we want to take that, we want to find the value of f prime of 2, all right? Just to determine if it's differentiable, okay? So we've got our function. I'm just going to rewrite it here real quick. So we've got x squared minus 4 to the power of 1/2, okay? I always like to rewrite that so that when I do the chain rule here, 1/2, bring that down, x squared minus 4 to the negative 1/2. In fact, I think this was a very similar problem to something that you might have seen in a previous homework 1 or 2 nights ago. And then don't forget to multiply by the derivative of the inside part. All right, and what happens is those are going to divide out, and I get something that says x over the square root of x squared minus 4. All right, there we go. We want to find this at f prime of 2. So what is f prime of 2 going to get us? So I'm going to substitute 2 in, 2 over the square root of 2 squared minus 4, and that's going to get me 2 over the square root of 0, which is 2 over 0. And as I'm thinking about that, 2 over 0 right there, that's undefined, okay? And you want to just like, anytime you're dividing by 0, that's undefined. Unless it's 0 over 0, that's in an indeterminate form. So therefore, f of x is not differentiable at x equal to 2. So we can see that happening, right? And so you want to make this connection right now, okay? We're going to look at more problems, but right now you're able to say, well, it wasn't continuous and it wasn't differentiable. All right. So let's look on to our next problem here. And we're going to do the exact same thing, okay, but a different function. And we're going to look at this now, and we're going to say, all right, we've got a new function here, and we're going to be graphing it. And so look at your graph, try to be pretty close, right? So it looks like it'll do something like that, and it's going to go up and across. Pretty close to what's coming up on your calculator there, okay? And so based off of this information, we're going to look at it the exact same way. The first part is f of 0. Is that defined? And so yes, f of 0 is defined right there. You see it right there. It is defined and it equals 2. Great. So now let's look at our limits. All right, so our limit of f of x as x approaches 0 from the left, that's equal to 2, okay? So you see it approaching 2 from the left side. And that equals the limit of f of x as x approaches 0 from the right. And you see it also from the right side, it is approaching 2 as well. And so they both equal 2. So that means that the limit of f of x as x approaches 0 from both directions is equal to 2. All right, so now what can we say? Okay, so since the limit of f of x as x approaches 0 equals the function at that point, and they both equal 2, so like everything's equal to 2, then therefore f of x is continuous at x equal to 2. So we can see it in the graph, and then you always want to go back to your definition that we had been using before for continuity, like what are the 3 parts that you need to show anytime a question saying, is this continuous? So you go back, you do that work, right? And we can see, okay, this function is continuous. Now we're going to see what is the value of f prime of 0. So the same thing, we've got f of x, and we're just going to rewrite it real quick, equal to x to the 1/3 plus 2. And what is that derivative going to be? So I've got, bring the 1/3 down, x subtract 1, so that gets me negative 2/3 plus 0. Okay, so if I just rewrite this real quick, I'm going to get 1/3 cube root of x squared. Okay, and we want to use that to find f prime of 0. Okay, so f prime of 0, that is going to be substituting in a 0, 1/3 cube root of 0 squared. And this comes out to be 1/0. All right, because you get 0 squared, 0 is all 0 in our denominator, right? And so again, this is not differentiable. Okay, so therefore, so it was undefined, so therefore f of x is not differentiable at x equals 0 because f prime of 0 is undefined. All right, and again, you want to make that connection. So here we had a function that was continuous, but it was not differentiable. So if it is continuous or if it is not continuous, that had no bearing on whether or not the function had a derivative at that point as well, okay? So what we can kind of say right now is continuity does not imply differentiability. So what actually ends up happening here, because we get 1/0, right, it's undefined. What actually ends up happening here, if we look at the graph real quick, is that you get a vertical tangent, right? The graph kind of twists right there. And so that's what's happening in terms of why we don't get a derivative. All right, here looking at our next example, we've got x to the 2/3 plus 2. We're going to be looking at this at x equal to 0 again. And your calculus senses might be tingling, but let's go ahead and graph this, right? And we're going to go here and we're going to graph this. Bam. Bam. Okay, hopefully you did on your calculator. You can see it for yourself. I'm not trying to trick you guys. Like, that's exactly what it looks like. And we're going to go and we're going to see, is this function continuous? Okay, so there are 3 parts. You might be looking at it like, look, Mr. Hernandez, that's continuous. But there's so much more. We've got to prove it. So f of 0 equals 2. So that means it's defined and it's equal to 2. So great. Number two, the second thing is we need to see our limits. So the limit of f of x as x approaches 0 from the left equals the limit of f of x as x approaches 0 from the right, and they both equal 2. So then that means that the limit of f of x as x approaches 0 is equal to 2. All right, and to our final part of differentiability, we need to state that both of those things are equal. So the limit of f of x as x approaches 0 equals f of 0, which they both equal, sorry, I made a mistake right there. They both equal 2, okay? So what does that mean? So what can we do? So we're going to say, therefore, all right, so therefore, f of x is continuous at x equals 0. So we've shown that. We can see that happening here. F of x is continuous, and you see it up here in the graph above, okay? So now we're going to get into differentiability. What are we going to see? What are we going to expect here? So let me just rewrite our problem again. So here's our function, f of x equals x to the 2/3 plus 2. And so let's find f prime of x. Bring the 2/3 down, x to the negative 1/3 plus 0. Okay, and I'm just going to rewrite this again. So 2 over 3 times the cube root of x. All right, perfect. And so then what do I want to do here? I want to substitute in, I want to find f prime of 0. What are we going to expect from this? So we're going to get 2 over 3 cube root of 0, and that is going to get me 2 over 0, which is undefined again, okay? And if it's undefined, that means, therefore, f of x does not have a derivative at x equals 0 because f prime of 0 is undefined. And so I want to take a second just to look at these two graphs, okay? So in this graph, like it's coming together, and what we call that in mathematics is a cusp, okay? So it comes together in like this sharp corner, right? And you cannot get a derivative at any cusp at any sharp corner. And the other thing that we had here is, again, it was continuous, but whenever it kind of turns into that vertical tangent, you also will not get a derivative at that point either. Okay, so we're going to condense that down into these two statements. So based on what we have seen, does continuity imply, or does differentiability imply continuity? And so for the first part, we'll say continuity does not imply differentiability, because at a point of inflection or a cusp, the graph is continuous but not differentiable. We saw that in our previous two examples. The second thing is that in order for a function to be differentiable at an x value, the function must be continuous. Okay, so if we have something that is differentiable, then it does imply continuity. Okay, students, so we're going to end the video here. Now that you have that big calculus drop, continuity does not imply differentiability, but differentiability does need to have continuity, okay? That's something that you're gonna wanna keep saying to yourself. Continuity does not imply differentiability. Differentiability does imply continuity. Okay, so keep saying that to yourself. You're going to fall into that trap at some point in your calculus careers, and someone's going to come over and say those words to you. Continuity does not imply differentiability. We've got another video left where we're going to hammer this home a little bit more. We're going to use it in some additional problems. So stay with it. And of course, if you do need any help, if you want to see more examples, please just reach out to me. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.